Good morning, chemistry, 2nd through 5th hours. Going to go pretty quick. There may need to be a pause sometime, or you may have to go back to the Moodle to be able to figure out where it's at. I can tell you you're going to need a notebook. You should also have out something to write with, and it would really be helpful to have a calculator. I'm going to whip through some things that you probably did if you took physical science. There may be a little bit more detail to it, and so I believe it's somewhat of a review, and you're going to have 4 of these to try when we are done. So the first thing, now that everybody's got their notebook, calculator, something to write with, ready? What happens when you add heat to something? Basically, one of 2 things can happen. 1 or 2. It's either going to heat up, get hot, or get warmer, or it might phase change, or change phase. What we found is, according to the whiteboarding, they don't do the same at the same time. This is where I would probably have a little demonstration, and I would probably get this little blowtorch going, but considering I don't have a hand that can do that or even light a match, I'm not going to. And I'd probably choose somebody in the front row, I don't know who it would be, and then I would get a blowtorch and I'd say, feel this. What does it feel like? It's kind of cool. I'm going to put heat on this. I'll do sound effects. Not bad for somebody who broke their ribs. Would you want to touch that? Of course not. It would be too hot. Same thing. Add heat to this. Feel this. Catch my breath. Would you touch this? Turns out you could. Oh, but be careful. If you touch that glass, that would, even though I didn't shine it or put it on there, that would be too hot to touch. So we have 3 substances that we did about the same thing to, which was add heat. 1 would be too hot to touch, still warm. 1, not so hot, and even the glass, too hot, even though it didn't come in direct. Apparently they all absorb heat at different rates. Today's not about then just telling whether or not they absorb. It's about the quantitative portion, keeping track of the numbers wise of how much heat goes in and what does it do. Those sorts of things that we were just dealing with. Water, that water has something called a heat capacity or specific heat of 4.18. Look at this unit. Joules per grams times degrees Celsius. Weird looking, especially the way I drew it. 4.18 joules per grams times degrees Celsius. What that means is it takes 4.18 joules to change the temp of 1 gram of water 1 degree Celsius. I know there's no ones there, but they're implied. Not so with steel. Steel has a different heat capacity. We kind of have a tendency to know that it gets really hot in the sun, but we don't really put numbers to it. Steel, it only takes 0.5 joules to heat up a gram of steel by a degree Celsius. 0.5 joules. You don't have to memorize these numbers. These are the types of things that are given to you. You just have to understand how to do the math. What about the glass? Glass, much, much less, 0.18 joules per grams times degrees Celsius. So what do we put, how do we kind of translate that? Well, if you put 4.18 joules of energy into some water, a gram of water, it'll only heat up by 1 degree Celsius. But if you put 4.18 joules into a piece of glass, it's going to be, I don't know, about, well, whatever 4.18 divided by 0.18 is, probably about 25 times warmer. It's going to change that much. So let me show you something you're probably familiar with. I'm going to write it pretty big letters, spread it all the way across a piece of paper so we can put some notes under there. Q equals little m times little c times a triangle, which I'll say delta T, capital T. Q, for some strange reason, is heat. It's usually measured in either joules or calories. M makes more sense, mass. And we generally you know what, we're sticking with grams. We could go kilograms if we wanted to make you multiply or divide by 1,000. I think we'll just stick to the basics. C. C is what's called the specific heat or specific heat capacity. I've used that terminology already. I've showed it to you a little bit. Here's one, here's one, here's one. And it's generally in, and I'm just going to keep this one in, joules per grams times degrees Celsius. Interesting, we could actually use degrees Kelvin as well, and we can use them interchangeably, and we don't even have to convert. And the reason is, well, let me get to the next part. Delta T means change in temperature. The delta is just a symbol in math that means that it's like the difference or a change in. We don't have to do negatives. In fact, we won't do negatives. If it gets bigger or smaller, we just subtract, take the difference, the absolute value, and it'll be in degrees Celsius. It could be in degrees Kelvin because the size of the degree is exactly the same. But you know what? Considering the circumstances, I'm kind of thinking I'm just going to keep it. We'll keep it in Celsius. Got to hit pause. That was my ride. I got to go fast. If you have to press pause, Mrs. Dobbin, you may do that because I'm going to crank up how fast I go. Next thing I'm going to do is just draw the heating curve that we've done many times so we can sort of refer to it. It's going to look like this. It's going to look like this. Looking familiar? This is at 0. This is at 100. This is for H2O. Other substances are going to behave very differently. Okay, so mention that thing called the specific heat. Specific heat for 3 substances. Ice, that's solid water. Liquid, which is water, and gas. Well, we already did the liquid one, 4.18 joules per grams times degrees Celsius. Ice doesn't heat up at the same rate. It only takes 2.1 joules to heat up a gram of water, degrees Celsius. And gas, it's somewhat different, but general idea in general chemistry is they are the same number. They're so darn close. It's 2.1 joules per gram degree Celsius. So what might a problem like this look like? I have $27 grams of water. 27. I'm going to use that every single time on my examples. The first example is ice. What if it were ice and it were at negative 45 degrees Celsius and I heated it up, heated to negative 12 degrees Celsius? How much heat would that take? You guys have done these. Q equals M times C times delta T. The heat that it takes is the mass times specific heat times delta T. So I simply take 27 grams times the specific heat of ice. Ice is 2.1 joules per gram degree Celsius times the change in temp for this one, negative 45 to negative 12, is a change of 33 degrees Celsius. 27 times 2.1 times 33 should equal 1871.1. What do I do for units? Well, it asked how much heat. Maybe it didn't. That's what it will say. But grams and grams cross off. Degrees Celsius crosses off. Joules is the only thing that makes sense. What if this 27 grams wasn't ice? What if it were liquid? Let's see. Let me just draw a... I'm going back to a different... I guess it doesn't matter. Liquid. And what if its initial temp was 8 degrees Celsius? Heated to 71 degrees Celsius. How much heat would that take? Q equals M times C times delta T. We still have 27 grams. This time it's liquid water. Liquid is 4.18 joules per grams times degrees Celsius. And the change in temp from 8 to 71, 71 minus 8 is 63 degrees Celsius. Put that into the calculator, 27 times 4.18 times 63, 7,110.2 joules. Same drill, only this time we've dealt with ice, we've dealt with liquid. Let's go with steam. What if we had some steam? Remember, I superheated some. I had it above 100. What if we had it from 100 degrees Celsius, just evaporated, heated to 110 degrees Celsius? How much heat would that take? Q equals M times C times delta T. Very methodical. It's still 27 grams. This time it's steam. That's 2.1 joules per gram degree Celsius. You wanted to memorize those. You'll use a little test-taking tool. Change from 100 to 110 is a grand total change of 10 degrees Celsius. When we multiply them all together, it's 567 joules. Okay. That dealt with how to do calculations here, and how to do calculations here, and how to do calculations here. Anything with a slope, because those are temperature changes, so we use MC delta T. What about there? What about there? What about phase changes? How do we do that? There is no temperature change, so MC delta T wouldn't work. Otherwise, our change of temp would be 0, and the answer would always be 0. And we know that the heat's doing something. So what am I going to write? What about the phase changes? What about the phase changes? Also known as the plateaus. Q equals MC delta T won't work. There's no change in temp. I had that written. I won't write it. Here we have to deal with two other things, not specific heats or specific heat capacities, but heat of fusion. And that's just a fancy way of saying things stick together, like freezing. And the opposite of that would be melting. So let's put it in parentheses, freezing or melting of water. We're dealing with water. And water, the heat of fusion, is 334 joules per gram. No change in temp, because when things freeze, let me go back up there. When things freeze, this is the freezing, depending on it, or it's melting, but it's also called fusion. If it freezes, it's fusion, and then the opposite of that would be melting. If you have a gram of ice, it's going to take 334 joules to melt it. If you have 2 grams, it's going to take 668. 10 grams, 3,340, and so forth. It's just a matter of multiplying by its heat of fusion. Got to press pause again. So, what is a sample problem? How much heat needed to melt a 15-gram chunk of ice? Assuming it was totally frozen and we're going to get it totally melted, 15 grams times 334 joules per gram, and that's going to equal 5,010 something or other. Well, grams and grams cross out. Joules it is. What about evaporation? Another name for that. It's called heat of, not quite evaporization, but vaporization. Heat of vaporization. We would call that the boiling, vaporizing, vaporization, Or if it was going in the other way, it would be condensing. If we add heat, it'll boil if we take it away. And that's of water. In this case, that is 2,260 joules per gram. That's a very big number compared to 334. Remember when I jumped up and smacked the ceiling and talked about how much more energy it took to smack the ceiling? It's about 7 times as much. And so I'm not going to be jumping up on tables anymore today or probably this school year. But yeah, we'll see. So how do we parlay this into a problem? How much heat needed to, let's say, condense? I could say evaporate, but let's say condense. How much heat needed to be, no, I don't like the way it's worded, and I'm in a hurry because my ride's coming. How much heat needed to boil 15 grams of H2O? Assuming it started at 100 and it ended as steam, but it's still going to end at 100. No change in temp. 15 grams times 2260 joules per gram would be 33,900 joules. How much heat would it take to condense 15 grams of steam? You'd have to take away 33,900 joules. So it's the same number depending on where we're going. We've now hit all 5 sections. We've hit how to go with changes in temperature, and I said that was there, there, and there, but we also know how to calculate whether phase changes, whether it's the fusion one, melting or freezing, or whether it's evaporating, which is called heat of vaporization. Therefore, we can put them all together. I'm going to show one of these. When we do these types, multi-step problems, you need to draw the heat curve first, because not because the teacher likes to see you draw, but because it helps you figure out how to do a multi-step problem. Here comes a multi-step problem. Okay, this will be on the piece of paper. I'm going to do number 1 on the piece of paper for you. A 65-gram sample of steam at 175 Celsius is cooled to liquid at 45. So what I need to do is this: sketch out the heating or cooling curve. Well, they told me it was cooling. Include the important numbers. 175 is as high as I need it. But I know that when you cool it off, it's going to get to a certain point and it's going to reach the magic number of 100. And then there's going to be a plateau. And then it's going to cool off again until it gets down to 0. And then it's going to be a plateau. And then it's going to cool off again. I got to go back. I'm reading the directions, and this is not a 5-stepper, so it never gets to 0, does it? It's only going to get to 45 degrees. So this is what tells me that when I look at the facts, 175 down to 45, it's only a 1, 2, 3-step problem. So I don't make a cooling curve because the teacher wants to see it. I make it to plot a plan for what's going to happen. I got to change its temp. That's number 1. I've got to condense it, which is that's number 2. And then I have to change its temp again, number 3. Every single one of these is 65 grams, 65 grams, 65 grams. So I got it all set up. All right. 1 and 3. See how there's a slope here? And there's also a slope over there. 1 and 3 are going to be the MC delta T types. M times C times delta T. So is this one. You don't have to write this little stuff, but some of you may choose to. 2 is going to be it's going to be condensing, but it has to do with the heat of vaporization. Heat of vaporization. So what I have to do is figure out how much energy it takes for each step of it, and then just add them all together. I'm going to get some numbers over here, add them all together. I'm going to do this one, and you're going to attempt 2, 3, and 4. The first one, the first segment right there, 65 grams, that's steam. That's an MC delta T. What is the specific heat of steam? 2.1 joules per gram degree Celsius. You don't have to memorize that. It's written in your notes. What is the change of temp? Careful here. Do not subtract 175 and 45 and think that's your answer. It's only going to change from 175 to 100 before something else happens. That's a change of 75 degrees Celsius. I'll put those together. No. Oh, darn, I do not have my calculator. That's okay. You guys can do that. This times this times this, and you write a number. Heat of vaporization, the second section, is different. I need to know how much energy to take away or how much heat to take away before it condenses. So that's deal with the heat of vaporization. Heat of vaporization, we're going from steam to liquid. That's 2,260 joules per gram that have to be removed. I'm going to put a new number over here if I had my calculator. I don't. Finally, what about the third segment? The third segment is also an MC delta T. Since it just condensed, it's now cooler than 100 degrees. This water is liquid. The specific heat of liquid is 4.18 joules per gram times degree Celsius. Its change in temperature is going to be from 100 all the way down to 45, and then it'll be done. 100 minus 45 is 55 degrees Celsius. I would have 3 different numbers, and all of them would be joules, 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 and when you add them all up, it's all going to be joules. You try 2, 3, and 4. They're similar to what we've done last year. Good luck.